Hey everyone, welcome to The Explainer. I am super excited to jump right into Chapter 9 today. We're going to be acting as junior scientists here, mastering the literal atomic foundations of matter so you can absolutely crush those upcoming exams.
Okay, let's take a really quick look at our roadmap. We're covering everyday changes, foundational laws, Dalton's atomic theory, bonding and formula mass, and then we'll wrap it all up with a summary and a quick quiz.
All right, Section 1, Everyday Changes.
So, have you ever actually stopped to wonder what happens when you dissolve salt into a glass of water? Or maybe when you mix baking soda and vinegar? Does that matter just vanish into thin air when it changes form? It's kind of a crazy thought, right? But it's exactly where our journey begins today.
Think about everyday stuff, like water. It undergoes physical changes all the time. Now, if you take a beaker of water, put it on a digital scale, weigh out some salt, and then mix them together, guess what? The final weight of that salt water is exactly the sum of the water and the salt separately. There's literally no change in mass during a physical change. But that begs the question, what about chemical changes?
That brings us to Section 2, Foundational Laws, the rules of the universe. We can actually prove how matter behaves during chemical changes with a super classic experiment. So picture this. First, we pour some vinegar into a flask. Next, we put some baking soda inside a deflated balloon. Then, we stretch that balloon over the top of the flask, but without spilling the baking soda in just yet. What we've done here is create a closed system. Nothing gets in, nothing gets out.
Before we mix anything, we weigh the entire setup. Then, the fun part. We lift the balloon, the baking soda drops in, and boom! We get that awesome fizzing. Or, as scientists like to call it, brisk effervescence. The balloon blows up with carbon dioxide gas. But here's the crazy part. Look at the digital scale. The mass remains completely unchanged before and after the reaction. No way, right?
So what this is actually showing us is a massive scientific breakthrough from way back in 1789 by Antoine Lavoisier. You might know him as the father of modern chemistry. He figured out the law of conservation of mass. Basically, matter can neither be created nor destroyed in a chemical reaction. Your starting mass, the reactants, will always perfectly equal your ending mass, the products. Okay, let's look at another historical puzzle. For centuries, ancient civilizations used this really striking red pigment derived from rocks. In India, it's called hingula, and in English, cinnabar. Now, heating cinnabar always produced two elements, mercury and sulfur. But here is the wild part. It always yielded exactly 86.22% mercury and 13.78% sulfur. I mean, it literally didn't matter where they dug the rock up from, the ratio was always exactly the same.
And this brings us right to our second foundational rule, thanks to Joseph Proust, the law of definite proportions. It states that a chemical compound always contains the same elements combined in a fixed ratio by mass. Honestly, think of it like baking a cake with a super strict recipe that nature absolutely never ever breaks. Pure water is always going to be hydrogen and oxygen in a fixed mass ratio, whether you scoop it from a river or synthesize it in a lab. So let's just pause and ponder for a second. Test your knowledge here. Do you think this strict recipe rule applies to just a random mixture, like, say, dissolving sugar into your cup of tea, or mixing sand and water? Well, the answer is absolutely no. And heads up, this is a huge misconception alert for your exams. Mixtures can be made in literally any ratio. You can make your tea as sweet as you want, right? But the law of definite proportions only holds true for chemical compounds. Their recipes are fixed by nature. End of story.
All right, let's move on to Section 3, Dalton's atomic theory.
So back in 1808, a teacher named John Dalton proposed a theory that pretty much changed science forever. He essentially described atoms like indestructible Lego building blocks. His theory had a few main points. 1, all matter is made of tiny atoms. 2, they are indivisible. 3, atoms of the same element are completely identical. 4, different elements have different atoms. And 5, they combine in simple, whole numbers to form compounds. Because, you can't exactly have half an atom in a molecule.
Now, even though we can't see them with just a standard magnifying glass, these tiny invisible particles are the entire reason these laws actually work. Because atoms are just rearranging themselves during a reaction. They aren't disappearing, mass is strictly conserved. Dalton's theory was basically the perfect puzzle piece to explain exactly why Lavoisier and Proust's laws made sense.
Which brings us to Section 4, bonding and formula mass.
So, remember from your earlier studies, atoms really just want to be stable, right? And they usually do that by getting 8 electrons in their outermost or valence shell. To pull this off, they bond in 2 main ways. First up, covalent bonds. This is when atoms share valence electrons, kind of like good neighbors. And second, ionic bonds. This is where atoms transfer electrons completely. One atom loses an electron, becomes a positive ion, the other gains it, becomes a negative ion, and, well, opposites attract.
Okay, let's actually calculate the total mass of these compounds. Specifically, the formula unit mass of an ionic compound like sodium oxide, Na2O. It's actually super simple. You just take the atomic mass of the element, so sodium is 23 unified atomic mass units, or just U, and multiply it by the number of atoms. We've got 2 sodium atoms, so that's 46U. Oxygen is 16U, and we only have 1 of them. Add them together, 46 plus 16, and boom, you get a total formula unit mass of 62U.
All right, grab your scratch pad for a quick knowledge check. What is the molecular mass of methane? The formula is CH4. Carbon is 12U and hydrogen is 1U. Go ahead and take a second to calculate that.
Got it? Okay, so if you calculated 12 for the single carbon atom plus 4 times 1 for the 4 hydrogen atoms, you should have gotten 16 unified atomic mass units. Awesome job if you got that. That is definitely a super common type of exam question, for sure. And finally, Section 5. Time to lock it in with our chapter summary and quiz.
I would highly recommend grabbing a quick screenshot of these at-a-glance bullet points for your revision notes. These are the absolute core concepts we covered today. We've got the law of conservation of mass, the law of definite proportions, Dalton's theory of indivisible atoms, the difference between sharing covalent bonds versus transferring ionic bonds, and of course, how to calculate molecular mass. If you understand these bullets, you have basically mastered the atomic foundations of matter.
Let's do one final, maybe slightly tricky exam prep question. If a chemical species has 11 protons, 12 neutrons, and 10 electrons, what's its atomic number and its mass number? Think back to our journey inside the atom. Remember, the number of protons always dictates the atomic number, so that's 11. And the mass number is just protons plus neutrons, so 11 plus 12 gives us a mass number of 23. Now, did you notice it only has 10 electrons? That means it actually lost an electron, making it a positively charged sodium ion. You guys did amazing today, but, as always in science, the quest continues. I want to leave you with this final kind of provocative thought to research on your own. Are there any changes out there that do not obey the law of conservation of mass? Like, what happens if we step outside normal chemistry and actually split the atom itself? Does Lavoisier's perfect law hold up in the nuclear realm? Definitely something to think about. Keep exploring. Thanks so much for joining me on this explainer, and seriously, good luck on those exams.